All right, guys. So one of the things that you're going to see, hopefully, as we begin to introduce this, is why I spent as much time going through transformation rules as I did. Because when you guys start to graph any type of function, all of those same transformation rules that we talked about for linear equations and absolute value equations apply for these as well. Okay, so let's set the stage here just really quickly, talk about what a quadratic is. A quadratic equation or quadratic function has the following standard form. Okay, so a quadratic means that it's going to be a highest power of 2 for your variable, for your x. And so the standard form looks like this. Y is equal to ax squared plus bx plus c. So this is, again, now notice it's different than the standard form of a linear equation. Okay? In standard form, if you write an equation in standard form, you're writing it with integer coefficients, and you set a capital AX plus capital BY equals C. That's the standard form for a linear equation. For a quadratic function, you're dealing with this form. And the one restriction is a must be some value other than 0, right? If a was 0, then you would have a linear equation. You just have bx plus c, or highest power of 1. Okay, so the other thing that you need to be familiar with on any types of functions is what the parent graph looks like. So the parent graph for quadratic is just x squared. And so let's take a look at what the equation actually looks like. Okay. An x squared graph is just a parabola. It's a U-shaped graph. And so based on this, all the different types of transformations that we've talked about will apply in this as well. Okay, so if you take the following transformations, okay, let's say we wanted to sketch the graph of the following. All right, if we wanted to sketch this graph, all the different transformation rules that we've already talked about will apply to this as well. Okay, so one, we have a vertical shift. And remember, a vertical shift looks like this. If you take your function and you add or subtract some value, I'll call it k, okay, that means that your whole graph gets shifted up or down. So in this particular case, here's our basic parent graph. In this case, do we have anything being added outside of the function? Now, remember, the function itself is the square. Is there something being added or subtracted on the outside of that? Yeah, the plus 2. So what we're going to do is we're going to take this graph, we're going to shift it up 2. And so, again, if we are looking at this parent function gets shifted up 2 to account for its vertical shift. Okay, then we also looked at a horizontal shift in our transformation rules. The horizontal shift occurs when there's a transformation inside. So f of x minus h or plus. Remember, that could also be a plus inside there. Is there anything that's being added or subtracted within the square of this function? No, it's just x, right? There's nothing. There's not a collection of terms in there inside this square. So in this case, there's no horizontal shift. Okay, after that, we look at the reflection. Okay, remember, the reflection occurs when there's a negative in front of our function. So is there a negative in front of the squared value here? Yeah. So if there is a reflection here, we're looking for, this is reflection across the x-axis. Another way to look at it is a vertical reflection. Okay, so we're going to take our graph right here, and at this point, it just gets reflected at its lowest point in this case, straight down, across what was the x-axis before the transformation rules applied. And then finally, so we account for the reflection here, and then finally here we can look at the vertical shrink or stretch. Of the functions. Okay, so now this is some multiplier, a coefficient in front of our function. And remember, the rules for this is if, and we're only dealing with the absolute value of that multiplier, but if it is greater than 1, then you have a stretch, vertically stretched. It becomes narrower or steeper. And then if the absolute value of a is less than 1, so if you have a fraction between 0 and 1, then you're going to shrink it, the graph, which will make it wider. Okay, so you're talking either steeper or wider for this. So is there any shrink or stretch effect taking place on this? Yeah, look at the number in front. Again, disregard the sign of it. Here. So if absolute value of a is greater than 1, this slash here is greater than, this is greater than 1. So if it's a number, if its value, again, disregarding the sign of it, if its value is something more than 1, then you're going to have a vertical stretch. It's going to be a steeper graph or a more narrow graph. And then if the absolute value of a, the coefficient or the multiplier of your function, is less than 1, then you're going to have a graph that is shrunken, and it's going to be a wider, flatter graph. So here we have a multiplication by, again, disregard the negative, but just the 2. So 2 is a value greater than 1, so is this going to shrink or stretch? This is going to stretch it, right? It's going to be a steeper function. So this purple function right here is y equals negative 2x squared plus 2. Okay, so we could sketch this graph just by using all the different transformation rules that we already talked about with linear equations and absolute value equations. Okay, now there's a couple other pieces of information that you're going to need to be able to identify specifically with respect to quadratics. And the first is the vertex. Okay, so the vertex of a quadratic equation can be found at the x-coordinate for the vertex can be found at the value negative b over 2a. So if you look at the standard form and you take the coefficient of the first degree term and multiply by a negative, and then divide by twice the coefficient of the second degree term, the leading coefficient, that's going to give you the x-coordinate of your vertex. And then your y-coordinate for that vertex, you'll just plug in. And I'll show you this in just a second. So if we wanted to confirm, we can see right here what our vertex is. Our vertex is 0, 2, but let's confirm that. If we plugged in our values here, so here are a, b, and c value for this function. What is the a value? The coefficient of x squared is negative 2. What's the b value in this function? There's no there's no x term, so the b value is 0. It disappeared. It took it completely away. And then what's the c value in this equation, this function? It's the constant, so 2. So if we plug these values in, negative 0 over 2 times a negative 2, again, it doesn't even matter here. The signs, despite they'll cancel, 0 divided by any number is 0. So there's the x-coordinate of our vertex. And then what we're going to do is we're going to plug that coordinate back in to our function. So if we plug in a 0 to our function, f of 0 is equal to, remember, the x's are just placeholders. So negative 2 times 0 squared is 0, plus 2 gives us 2. So our vertex is going to be the point 0, 2, which confirms what we got in our graph just by using the transformation rules. Okay, once you have, or in addition to the vertex, you also need to be able to find what's called an axis of symmetry. And the axis of symmetry is always going to be a vertical line, and the vertical line is just going to be the equation x equals, and then it's whatever the x-coordinate of your vertex was. So negative b over 2a. And it's always going to be an entire equation. Okay, so the axis of symmetry for this is going to be x equals our y, or the x-coordinate of our vertex was 0. And so what that means is this graph will be a reflection across itself at this vertical line, x equals 0. Okay, so that's the axis of symmetry. And then the final concept that you need to be aware of is whether your vertex is a maximum or a minimum value. And so when you look at this purple graph here, is this vertex the highest possible y value, or is it the lowest possible y value of the graph? In this purple graph, it's the highest possible y value, so that's a maximum. If we were talking about this parent function, would the vertex be a maximum or minimum? Here the vertex would be the lowest possible point, so that would be a minimum. All right.